Hello and welcome to another edition of Vibrations. I'm your host, Taylor Ringgold, and today we have two awesome guests to talk about a great topic. First, Wes Wigglesworth, who is the product manager of TMC. We also have Neil Fitzgibbon, who is the senior business development manager at Taylor Hobson. Gentlemen, thank you so much for joining me today.
You're very welcome. Thank you for having me, and I'm looking forward to the conversation.
Yeah, thank you very much, Taylor. Always up for an opportunity to talk about our exciting products.
All right, so let's talk about these amazing products. And Neil, I'm going to start with you. So the LufaScan 850 HD, tell the people exactly what this thing can do and how important is it to this industry?
Okay, that's a very good question. The 850 was is a game changer in optical metrology. It's set new or broken boundaries and limitations that were previously there. It's a big instrument. It's capable of measuring optics from as small as 1 millimeter up to 850 millimeters in diameter, which is a pretty challenging requirement for any instrument. And as well as that, it can also handle load variations between a few hundred grams up to 350 kilos. So that makes it's a very challenging instrument to be able to support from a structural point of view as well. But certainly it's opening new doors to optics manufacturers that can now measure bigger parts. There's more versatility, and we're getting levels of accuracy that previously were only available on instrumentric type measurements. So it's a bit of a game changer.
One of the things that's unique about it in terms of the support and the vibration control is that we really worked from the ground up and focused not only on the supporting the granite with pneumatic isolators, which are historically very good isolators for high frequency, but we also understood that there would be a low frequency component to this that needed to be addressed, and in designing a solution to address both, we have two stages of isolation, which is critical, particularly when you hear anything nanometer scale with this instrument. It's also the other thing that was important to understand when we were approaching this was the size, just the overall size of the instrument and the weight of the instrument. It's very large scale, as Neil said, can work on very large pieces as well as very small. So we needed to be able to scale up to that with a system that would support that payload from a capacity standpoint, as well as work down to very, very low frequencies and very, very low input coming from the floor, because it's very sensitive to vibration at all frequencies and the very smallest of vibration coming from a building or from the floor.
Neil, why did they choose to work with TMC to design the vibration system? Why didn't you guys just do it on your own?
That's another good question. I think it was important that we turn to the experts in vibration control. Obviously, we've worked with TMC in the past, and as Wes said, this instrument, by virtue of the size of the instrument, the weight, and the variety of loads that it needed to accommodate, as well as those loads being dynamic as well, i.e. there's moving loads on there. All of these present a real challenge when it comes to a structure that is supported with anti-vibration mounts or a platform that can handle it. But equally, the instrument is incredibly sensitive, as Wes said, down up to a nanometric level with vibrations. And it was a really valuable working relationship. We knew that if we went to them, they'd be able to look at what our needs were, understand them, and come back with a solution. So they made a lot of sense to work with the company, with TMC.
Wes, when you heard that they were coming to you guys for help and to get to figure out the right design for the vibration system, how did TMC feel, and how did you feel exactly to work together with such a company like Taylor Hobson?
First of all, I think they made the right choice. TMC started in the vibration control business back in the 70s, and we've been working with engineers and scientists to design precision instruments, really the world's most precision instruments that are used in a various number of applications. And, Taylor Hobson has always been a leader, particular with optical-based instrumentation. So, if you go back over time, we typically are dealing with a lot of instrumentation that use electron beams, and optical instruments, have historically not been as sensitive to very low frequency vibration. But we know that, as time goes on, the demands of these instruments just continue to increase. So, interferometry and optical based instruments, they're just getting more and more sensitive, and also, looking down to resolve a much smaller, geometry. And that's the case with so many different applications, whether it be, chip manufacturing, semiconductor chip manufacturing, or optics, or molecular biology, things like that. So, it was really exciting to work on an instrument that Taylor Hobson is designing, because it was somewhat new to us, but we completely understand the challenges, because all the challenges are very similar. High payloads, very low input coming from the floor, not just low frequency vibration cancellation, but cancellation over a wide bandwidth of frequencies, because it's not just the floor, but the instrument itself has a frame and has resonances, and you have to know how to deal with that, in addition to what's going on up on the payload, because there's moving parts in the payload that you have to understand and address. So yeah, it was a great opportunity for us to work together to develop this next generation cutting edge solution.
You even mentioned the challenges that can go along with such a project like this. And I think that's what makes a good product at the end of the day, right? When there's not every revolutionary product has an easy route to making the product. And I think that's just part of the story of how you guys work together to make such a product like this. Neil, this question is for you. What would happen if you didn't control vibration? If you can tell the people what exactly that could do for the product you have, and just the overall question.
Yeah, I mean, it would have a catastrophic effects on our measurement. I guess to put it in context, the instrument, just a bit of background here, the instrument works by rotating an optic, and then we measure with a non-contact probe, and we spiral across the surface of the optic to essentially scan that whole surface. Now, when you're measuring very small parts, the measurement cycle time is very short, as you can imagine. When you're measuring 850 millimeter diameter parts, the measurement cycle is significantly longer. So therefore, if you've got environmental impact, you're very sensitive to environmental impact such as vibrations, because any fluctuations in the instrument transmit directly through to the probes, which are on long arms, etc. And this will then come through in the measurement. And what's important is when we give our customers a measurement result on our instrument, we have to be as sure and as confident as possible that what they are seeing is a result of the surface that has been measured, and not a result of the environment around it. So if we are getting a lot of especially low frequency vibrations coming through, and the measurement's taking 10 minutes, 15 minutes, that can put what we would call mid-spatial frequencies into the measurement that could actually be a manufacturing error, and we don't want to combine the potential to miss or add errors that aren't actually there on the part. So we need to be sure when we're measuring, all we're measuring is the surface, and we're not actually giving any results that include anything else, in this case, vibration. So it's absolutely critical that we remove all of the vibrations is critical to the instrument. And that's where I think we've been calling it a double stack system. Wes has obviously got a better name for that, but the combination of the two different types of anti-vibration platform allowed us to remove all of the frequencies that we needed to, or that the work potentially, could potentially impact our measurement accuracy.
How hard is it to keep things almost, it's hard to, the word perfect is such an interesting word, right? Because nobody is perfect, but you have to be perfect, right? You have to be, you can't make one little mistake. How hard is it to not have a mistake like that?
It's very hard. And I mean, we use perfect, you're right. Perfect. If we could be perfect, then we would be by far and away the market leaders and there'd be nobody else out there. But we have to get as close, as you said, to perfect as possible. And it is a real challenge. And on an instrument at this level, where we're measuring a diameter of 850 millimeters down to 100 nanometers of form error over the whole area, it's absolutely vital that we can eliminate all of the external factors that could impact that. We can handle the stuff that we do ourselves, and we know our technology from a referencing framework point of view. But that's where we need experts like TMC to come in and give us direction and support to get the parts go, to have the impact that we can't handle ourselves.
Sometimes I want to say this the right way. Sometimes companies like both of you guys, you might not want to work together on certain things. You want to try doing it on your own, but when you could honestly talk to yourself, say like, hey, look, we do need the help, and TMC is helping you so well and so much. Wes, if you can talk about why original equipment manufacturers should work with TMC into designing certain products, because I'm hearing a lot of great things about what your company can do from Neil, but maybe you can tell more about what TMC can actually do to others.
Sure. Yeah. So, like I said, one of the things is that we've been doing this for a very long time. It's really a focus of ours. We have experts in the field of vibration control. And when we approach a project like this and designing an instrument, working with a company that's designing a precision instrument, we know the information that we need to gather. And it's more than just vibration sensitivity. Obviously, that's a main component, but it's important to also understand the requirements of the instrument from a throughput standpoint, to understand the parameters of the payload. Payloads can be very dynamic. They can be static as well, but a dynamic payload could have a moving stage that imparts very high forces on an isolation system. And if you choose the wrong isolation system with respect to the dynamics of the payload, it can really set you back, not only in designing that instrument, but it could have impacts on the throughput of that instrument, which ultimately you need to have high throughput and high yield successfully without imperfections. Talking about being perfect, but without imperfections in the measurement. So we understand a lot of these applications because we have worked on so many different types of applications, whether it be optical instruments or electron beam instruments, lithography tools, different instruments that are used not only in inspection, but also in precision machining, lithography, tools that are used in, I mentioned molecular biology earlier. So these are things like electron microscopes, very, very high power electron microscopes that are working down to smaller than nanometers, angstrom level resolution, where the very low frequency vibration cancellation is required, as well as higher frequency isolation. And this, we've referred to it a little bit, but it's 2 stages of isolation, or a hybrid, where it combines passive pneumatic isolation with active vibration cancellation to that's really the only way to achieve the level of performance that's required for these very highly sensitive instruments.
You just mentioned the 2 stages of isolation. To tell our viewers, is that always required?
Well, if you had asked me 15 to 20 years ago, I would say, well, no, not very often. But today it's required more and more often. And the reason is because you have a pneumatic isolator, which is essentially an air spring, very, very good at attenuating vibration above a certain frequency. So like 10 hertz, typical machine vibration, a lot of different types of building vibration is mitigated with a pneumatic isolator, but it's above a certain frequency. When you get down to low frequency vibration, which comes from footfall, just people walking through a building, road traffic outside, automobiles, trains, there's a lot of low vibration input coming from up through the floor. And as these instruments get more and more sensitive, or they're resolving a smaller spot size, they get more and more sensitive to that low frequency vibration. And that's when that second stage of isolation is really required, to work down to very low frequencies below 1 hertz and input levels that certainly humans can't feel. But when you're talking about, it's almost like, I guess a good analogy is, if you're looking for in Manhattan, you're from New York, so you're looking for an ant in Manhattan from a satellite, similar kind of resolution or scale. When you're talking about molecular biology and very low frequency, or even today's chip manufacturing, 5 nanometer, you hear about 5 nanometer or 3 nanometer process in the semiconductor industry. Well, it's very hard to find a defect in that if you're not, particularly if you're not canceling very low frequency vibration.
So that's the detail that I needed just from that one simple question. That's why you guys are great, because I can ask one little question and then you guys can elaborate on and give so much details for the people that are viewing this. And my last question for the both of you, this is the same question for both of you. So Neil, I'll start with you. When you guys are making this type of technology, and this is revolutionary technology, by the way, to let everybody know, how does this make you feel? And also, what do you see that could be like for the future of the industry that you're working in? Like how beneficial is this piece of machinery and what you guys are doing? Because, at the end of the day, you guys are making products for the future and to better the future of your industry. So, how important is this product in general?
I'd say very important. The optics are changing in their uses, and they're becoming. I'd like to think, obviously, I'm biased, but it's probably one of the biggest growing areas of technology. That's not just in your mobile phones, which have got obviously really high precision cameras in there. It's your webcams. But it's up to, internet satellites. The communication links for internet satellites are actually based around mirrors or optics. But it goes to another level, and that's what, the shapes that need to be measured now to give these new levels of technology legs, if you like. They can't be measured easily by the existing optical technology that's out there. That's why at the beginning when I said the 850 is a game changer, it really is, because the versatility means that the one instrument could measure almost an infinite number of different shapes of parts, whereas traditional technology would have meant you'd have one instrument specifically to measure a certain type of optic. So you can imagine that opens up doors to optical manufacturers to develop such a wide range of parts that could go into medical applications. They go, there's semiconductor applications that they're driving now. Automotive applications are massive, as you can imagine. Satellite communications, telescopes. Some of the 850s that we've built so far are being used for telescope applications. But it's giving the industry the flexibility to evolve how they design optics, which in turn optimizes and increases the performance and increases the functions that we can get from them, which I think, ultimately we all benefit from. So it really is an important instrument in the industry. And, certainly I can only see things getting bigger and more involved, and we're going to have to keep the working partnership with instruments of this size going up as the challenges come with companies like TMC.
One thing that's really exciting about being part of TMC is this evolution of vibration control. So I talked about pneumatic isolators, and really when we first started designing solutions to go into machines for original equipment manufacturers, it was pneumatic springs, which is our gimbal piston isolator, and that was good enough because of the technology that it was supporting at the time. And people hear about Moore's law, and that alone has really driven the geometry of the semiconductor industry and the resolution of the instruments continuing to get pushed to its limits. And the exciting thing about the low frequency vibration cancellation system, namely our Stasis product, is that it was originally developed 20 years ago, almost before its time. And I would say over the past 10 years or so, it's really seen the applications that it was designed for, because the resolution of these instruments continues to improve and get to, like I said, angstrom level precision. And TMC really is, has a unique solution in the Stasis product, because it's really the only commercially available solution using a piezoelectric actuator and inertial sensors in this particular architecture, canceling very low frequency vibration, designed to work specifically with tools that also require pneumatic isolation, because really you need both, and you need to know how to combine the two. And it's just been exciting to see all these applications that need it. And we continue to work on so many different unique applications. Taylor Hobson is a great one. The Lufoscan 850, the LS850 has been one of these very exciting projects. And, we're not just standing by waiting for new applications. We continue to develop our technology to be able to work with exciting engineers and scientists on the next generation technology is also a very exciting part of it.
Well, Wes, Neil, thank you so much for joining me today. I learned a lot myself, and I know the people watching this have learned a lot as well. Appreciate everyone stopping by. My name is Taylor Ringgold, and we will talk to you guys soon.
Okay. Thanks, Taylor.